If you have a chance, please do start your assignment 3, okay, to be faster, so that, okay, if you have questions, I can answer in time, okay. As I mentioned, the last semester, last year is one of the projects that student has, I think they do not understand the idea in time, okay. So if you can, it shouldn't be that difficult, okay, but it's not something that you have exposure previously, I think, so that take some clarification, okay. So today, the goal is we'll spend 2 lectures on one of the important techniques, very practical as well, okay, called Monte Carlo, okay. So today we'll talk about the sampling, okay, and a lot of the unknown. If you have too little knowledge of a problem, the Monte Carlo is one of the very useful tool in trying to find out the property of the problem, okay? And these include, we have always want an initial guess, right? So we have all these nonlinear solvers, optimizations that we need the initial guess to start, okay? Whatever method we're using. How do you get that initial guess, okay? And Monte Carlo is one of the most popular ones, okay? And I'll go through and tell you that how Monte Carlo should be used, and so that this is something, it is actually originally, okay, Monte Carlo is developed for a optimization problem, okay? So the problem is, but just saying that, okay, just saying that is even get a very rough sample of initial guess is many times out of the capability of our today's computer, okay? Saying that you have 30 parameters in the least square fitting. And this is not strange, right? Even consider a car, okay? You have a car that you are designing. 30 parameters for optimization is not strange, right? You have all the shape of the car, engine, piston, how the heat is going to circulate and things, right? So 30 parameters is not strange at all for any engineering design, okay? Say if you want to generate an initial guess, okay, not the optimal solution, okay? Just the initial guess that we would like to have for an optimization problem for that 30 parameters. Each parameter you have 4 possible values. It's not the optimal value, it's just the initial guess, okay? There are 4 possible values for the initial guess. And that number is not something you can deal with, right? 10 to the 18 is not some number that you can use, try 10 to the 18 initial guess and try to find out the solution. It's simply not possible, okay? And many times, if you're playing games, okay, playing games like cards, okay, you only have 52 cards. Say you are playing, I don't know if you still know solitary. You know, okay, good, okay. So there are sequence of the card, of things, right? What are the number of combinations, okay? If you want to develop an expert thing to predict, how do you always be able to have a strategy to win? This is the operation space, right? That's, again, not possible, okay? Sorry, 52, sorry, 52, this is not 10 to the 52, 52 factorial, okay? So 52 factorial is about 10 to the 68. Okay, so it's a typo, sorry, okay. So again, it's not possible, okay, even for, so you probably see many movies about casinos. People have ways to explore, to predict what cards are coming, okay? And those minds cannot be using an exhaustive search. So it's the more famous now for the Go, right? So the for the Go game, right? It's not because exhaustive search is not possible. Because exhaustive search take this kind of operation, okay? Factorial grows so fast, so it's not possible, okay? So how can we sample it, okay? How can we sample? This is a problem puzzle the both mathematicians and physicists for a long time, okay? Until these two guys, okay? These two guys are not Nobel Prize winners, but those are the reason to believe the Nobel Prize has errors and big errors, okay? So these two actually figure out what I'm going to teach you today is the Monte Carlo sampling, okay? This is out of the Manhattan Project, okay? Manhattan Project to figure out how the nuclear reactors and the bombs, okay, that we have today, okay? And this guy, okay, that time a Wisconsin professor, later on go to USC, is in charge of how do I prove the stability of that nuclear reactor. Okay, for sure that problem is way too complex and way too important, okay, not to know the error. Okay? He's designing a nuclear reactor, and if somehow he doesn't know the bounds, you can see that can be too bad, right? So he was in hospital, real story, okay, and playing solitary indeed, okay. And he figured, and he say, okay, this is a way that I can do statistical testing for a unknown problem, okay. Then he's after that, he presented to the smartest guy in the whole world, probably in the whole history, called John von Neumann, okay. Together, they figure out this, how to provide this sampling method called the code name. It is Manhattan Project, okay. So everything has a code name, okay. And this code name, these guys are funny because Monte Carlo is where his uncle lose all his fortune that in Monte Carlo of Morocco, and then he has to come to the States, okay. He's Polish professors, and lost all the money. His family lost all the money. He came to the United States, okay. Anyway, so they call the code name Monte Carlo, okay. And this is, to me, that probably he's the initiator, and John von Neumann is the person who has bring the full reality of the Monte Carlo method, okay. So most of the things we know today about Monte Carlo is by John von Neumann, okay. So, and as I mentioned in my notes, okay, please, if next time you go to Princeton, please do visit, okay. Do visit John von Neumann's his house, his lab, his all the thing is preserved. Okay, so it's one of my favorite. Okay, now don't only walking on the Albert Einstein's thinking trail. Okay, but also go for John von Neumann. Okay, it's a very to me actually totally debatable whether he has even more contribution than Albert Einstein. Okay, so the person called Wissner, okay, compare him and Albert Einstein. He say there's no comparison. John von Neumann is much smarter. And Wilson saying I'm not crazy. Albert Einstein is my brother-in-law. Okay, so he's that smart. Okay, and yeah, read the wiki page. Okay, about John von Neumann. Okay, he's a genius of our generation. Okay, but he died at the age of 53. Okay, so you can probably explain that he didn't get a Nobel Prize because he lived too short. Okay, fine. Okay, but he lived pretty long. Still don't get the Nobel Prize, which is one of his most famous invention is not the Monte Carlo. He's all the if you like the movie Men in Black, most of the idea is Ulam. Okay, the nuclear propulsion. All this, even the Orion, okay, the project that he is working on the Los Alamos lab for the space exploration is called Orion, and the Orion become the Man in Black, developed the movie, okay. But many of the space travel inventions is by this guy, okay, Ulam, okay, a Polish scientist. He's Hungarian, okay, Hungarian, okay. So the idea is not very hard, okay? The idea of Monte Carlo sampling is that if I have a way to generate a test case for a random variable, okay? So let's denote it as V, okay? I don't know much about V, okay? I don't know about its distribution functions, okay? Then I don't know about its mean, I don't know about its variance. Okay, but I can get some samples of the legitimate testing case of that random variable. Okay, saying that a car design, okay, that's 30 parameters, okay? These are the initial guesses. Those are the possible parameters, possible values for those parameters. Good enough, okay, good enough, okay? So this is something that I have V, so you know, you have either a way to know whether this is a possible case of that random variable, or you have a way, have understanding about some property of that random variable, okay? But you know very little about the distributions, mean or variance, okay? The goal is to use the presently available testing case to know the distribution function, the mean, and the variance. Okay, so you understand, you can also use the V test case, how to generate moments. Actually, every moment of that random variable can be estimated, okay? Mean for sure is the first moment, and the variance the second moment. Okay, you can go for higher moment if the moment of the V has physical meaning, okay? So you can use that to do that, okay? So it is established, it's very simple, okay? So in a way, if I average the test case I have, and I call it this head A, okay? And I have a bias that's the present estimate minus an A, I don't know, okay? This is the true average of this random variable. You don't know A, okay? But you call this guy, right? This is something you have. You have N, big N of tests or samples. That's what you have, okay? And you calculate the average of that, okay? And the bias, right, against the true average, which is something, this is something you don't know, okay? Because you don't know A. You don't know this big A, okay? So, but this is called the bias of the present estimator, okay? This is something I can do, yes?
How do you figure out N? Or is that just something?
No, it's the availability that you can test.
Oh.
How much time you have to generate the test cases.
Okay.
Your next slide tell you the larger the N, the better. And how large is the N and how much better you can get is also bounded. So Monte Carlo sampling is a way that it's not that people don't do this before Ulam and John von Neumann. Is they put the statistical bar. If you do an experiment, this is the error bounds. Okay, sure, you know, you play a game, you play chess, you play Go's. You optimize, you want to win. How do you learn? You play again, one time, 2 times, 3 times, collect it, right? There's a behavior you try to learn, right? So the more you play, the larger the N, right? So that's we already do that. If you something that you don't know the answer, what do? You test it. You test it and get a feeling out of the thing you want to know, and you get the average experience. Monte Carlo, the contribution is he tell you what is the error you are dealing with. Okay, so this is a common human behavior. You just that for engineering, I need to know the error bar. When I do N test, right? I have a collection of N tests. What is the error bar I'm dealing with the true events? Okay. Okay. So even we do not know Rn, okay, these are the property of that bias. Okay. First, the expectation value of that Rn is 0. Okay. What does that mean? That means that the VKU randomly generated have an equal probability to be above or below the true mean. Right? You take it randomly, right? You take your test randomly, and then if your test is truly random, then the probability it is above or below the true mean is the same. So the expectation value of your Rn or the bias is 0. Right? That for sure, these imply, right? They imply that I need a good random guess. Right? I do have a bias in my bias, then the problem will be wrong, right? Because the expectation value won't be 0. Okay, I'll show you an example. You will know exactly what I mean. Okay, but if truly random, right? If your choices of the testing cases is random, then the expectation value of that is 0. Doesn't mean the present n test will give you the correct A. It doesn't mean that. Okay, it means the expectation value of your present test will be equal to A. Expectation value, okay, the one you calculated may not be the true A, but the expectation value will be 0. Okay, so this is not astonishing. Okay, the more astonishing thing is this. Okay, the variance of that bias is the true variance divided by n. Okay, that also means, right? So if when n is very, very large, and then this you will get this will always go to 0, but with the finite n, you can estimate what is the variance, what is the unknown true variance of the problem you are interested in. Okay, this is easy to understand. This is the main contribution of Zhang von Neumann. Okay, so I cannot prove it to you. Okay, in a short time. Okay, sorry. Okay, but in either Bindou's book or wiki page, he provide a large sections of proof. Okay, so if you're interested, okay, the variance of the bias is the true variance divided by n. This is the spirit of all the Monte Carlo simulation. Okay. Okay, let's take that as granted and leave that for your future exploration if you want to understand the mathematical proof for this. Okay, but once this is written down, then the next theorem then is easy to understand, is that when n go to infinity, okay, then just like everything, okay, if it's anything with enough randomness in the nature, large number theory tell you it will approach a normal function. Okay, if it's truly random, and like you taking a toss of your coin, you do enough, okay, the distribution eventually will be this normal distribution. Okay, okay. So these three are figured out by Zhang von Neumann. Okay, so let's see, not a lot of thing has been there, but this is so powerful in a way. What does it mean? Okay, what does it mean? Is that now we do not know A. We do not know the distribution of that random variable. We only have n samples, right? But we can have an estimate of its average, right? Just by calculating the present average. And I know my error is about this, right? Even better, okay? We can think the bias that we have is approximately this distribution, okay? It's the standard deviation, okay? Standard deviation times z. Z is just a normal, standard normal function, okay? This is standard normal, okay? This is the standard normal function, okay? And the divided by the square root of n, so that this will come up with the second property, right? This will come up with second property, okay? So even I do not know the distributions of V, but the way I estimate it, okay, the way I estimate it, it will have a Rn, the bias will follow a normal distributions with normalized by the square root of n. Okay, critical, okay. And its own deviation is the prefactor. Okay, I'll show you this is a little bit difficult to swallow, but in the example you'll understand. Okay, in the example you'll understand. Okay, so this is you can with the present n test in your hand, you can have that much understanding of the bias. Okay, and from that bias you can understand any moment of this random variable. Okay, this is what it means. Okay, I'll show you with this clear example. Okay, so it's the power. Okay, the power of Monte Carlo right? As long as we can do N testing, we can tackle a problem. We know very little about its behavior, like the nuclear reactor that this Ulam and John von Neumann are working on. They know little, but they can do testing, okay? Do tests and understand the behavior, okay? As I mentioned, right, many of the optimizations to extract parameter extractions, one of the purposes is that there are things you cannot test, but you would like to know them, okay? And Monte Carlo can do that for you, okay? Something that I can do something within my present ability of testing to understand when the nuclear reactor will explode, right? That's something you cannot test, okay? But you can do present tests to figure out the behavior, okay? The limitation is, okay, the error is go like this, n of the 1 over root n, right? So if you want to if n is 4 times larger, you only improve accuracy by 2 times. Okay, this is even worse than bisection. Bisection, you make a bisections, right? Search. Bisection improve, right? 2 times each time, right? But the Monte Carlo is even more inefficient than that. For sure, I mean, you are paying something that because you don't know anything, right? In bisections, I can evaluate the sign of that function. But this one, I can only generate random variables, right? So this, the convergence is even slower. Okay, so let's use an example to deal with it. Okay, I'll come back to this slide a little bit later. Okay, so let me go for there. Once you get the examples, then this is much more meaningful. Okay, let's calculate this pi, okay, by using Monte Carlo. Okay. In this one, I know if I have a half circle, okay, and if I shooting darts, okay, and if your shooting darts is truly random, okay, you choose a random x and random y, you can understand the behavior of pi by how much is within this half circle, okay? Each dart you throw is an experiment. In that experiment, you can make a judgment whether it's within that pi over half or it missed, right? This is called the rejection rule in Monte Carlo. I don't really know how the darts, right? I don't know the true probability, which is pi over 4, okay? Which should be pi over 4 in this, but let's regard you don't know pi, okay? So you don't know the probability, okay? Just by throwing darts, okay, you can understand what is pi, okay? So let's write this very simple code, okay? This is something doable in 5-10 minutes. Okay, let's write some very simple code. Okay, and let's calculate your pi. Okay, your Python or C should give you a similar function called random. Okay, a random will return you a uniform distribution between 0 and 1. Okay, 0 and 1. So you use that to see if you are within the circle. Okay, within that half quarter circle. Okay. And then that using the rejection rule, you can calculate the pi, okay? And for sure, you can know how good it is, right? So this pi with a different n, okay, you have a pi built in your language as well, okay? You know exactly the error, right? So plot it out, okay? For n equal to 10, what is the evaluation of pi? When n is 100 until 10 to the 6, okay? You can see that how good is your pi. And then I'll come back to why this is, you can see the Monte Carlo implementations in this one, okay? you should get a case of n equal to 10. Okay.
N is equal to 10 was around 4. The value of pi was around 4.
Okay.
For around 10,000, it's 3.14.
10,000. How about can you as you see have it run the a million case?
But it's still running.
Still running good. Okay. You either record the tens case, this is the progression, but you see a million will take the most time. The other will just take no time. When you report to me, please report the one that minus the true pi. Report to me the error. Okay. I am going to take a poll. Okay. So let me collect Prandeep's value first. Can you tell me the error? Just two significant digits is good enough.
For 10, it's
10 is what?
minus 0.34.
Minus 134?
0.34.
How about you come up and copy for us? I have an important message for this, okay? It's not that I want to do this to kill time. There's a very important message I want to tell you. Take your time. Others are. I need to collect 3 people. You have the number. Okay, good. You sure? Increase. Okay, sure. This one is too good, but that's okay. Sure. Okay.
Thank you.
Yep. Can I have another person record this number for me? I have a message, very important message. Okay.
My random number is returning a huge value.
Not between 0 and 1?
No.
Really? How about the rand?
The random,
So-
the random itself.
There are 2 possible things. One is called rand. You're using this. The random is not supported.
C++.
How about, is random supported?
I think rand is supported. Random is.
Yeah, random is 0 to 1, right?
No,
Should be.
It's not zero number. It's
Oh, random.
It's a random integer?
Yeah, random.
Yeah, it's just integer, so you need to do some operation like mode and divide it by the same mode.
Right. Okay. If
By the maximum.
yeah, you can, okay. You can deal with using this. If a random number you don't know is between 0 and 1, you can transform it by this, okay. Mode it, see, as Minda described. Okay. So this is Python?
Python.
Python gives you a random that's 0 to 1. I thought this is a random integer, but random, DOM, it's in C++, it's a standard 0 to 1.
Random.
Random. Not rand. Random. Right, just as I There should be such a function. You for sure need the mass.h. Is there such function? Is it random?
Random means in the STD library.
Okay.
No.
And is that between 0 and 1?
No,
Okay.
there's nothing between 0 and 1, I guess. So it will just generate some integer in C++.
Random integers. Okay. So you have to mode it. Okay. You have to go through that. Go through these internal calculations. Okay. So you just get the random, okay, and mode n, and then return that divided by m again. Okay.
Yeah.
You choose a large m, mode m, and then return that thing divided by m. Okay. This will give you a if you just give you an integer, okay, a random integer. So this is one way to get a random number between 0 and 1. Funny, they don't support the random number.
You can change it to a double and then divide by rand max. It'll also give you a random number.
Okay, do you have that?
Yeah. I mean,
Do you have the number?
You have the maximum number.
You can rand and then just
Okay.
cast it to a double and then divide it by rand max, and that should give you a random number between 0 and 1.
Yeah,
Okay,
sometimes
okay.
that value is
That's
not
another way. Good. Okay. Do you have this error?
No, I'm doing it.
Okay.
So what I think you can do is just use mode, like if we want to have two digits after 0, mode 100, then divide by 100.
The m needs to be large, huge.
Yeah, you can like mode 10 million, then divide by
Right.
10 million. That will also work.
Not exactly. Okay. If you truly want to preserve the randomness, it has to be a prime number.
Right.
Prime number, right?
Oh.
A large prime number. There's a reason to it. Okay. Anything that can be divided by the mode will introduce a bias.
Oh, okay, yeah.
So
It might be.
yeah, has to be a prime number, right? But that's okay. You can tell us how you. This is the random function that the Pradeep used within Python that gives the 0 to 1. Okay, give me a number that just tell me what is the random number generation you use. That's fine. Okay, come up and fill up the other column. Okay. Anybody ready even to 10 to the 5th, okay, can come up and give me another column. Hello, come on. Write it down. And this is what language? Python. Okay. Yes. Use the same random number that he called in the Python library. Hasn't finished the last one? So you have the same coincidence. Interesting. Is there another person? I need 3. Another person can come up and document the very last column. That's okay. That's okay. This is Python. Python. Anybody have a third column? They can come up. Anybody finish this? Yes. Does Perga have one? Come on. And that's in MATLAB. Okay. Okay. 7.8, right?
Yes.
Okay. And the Prandeep, is this O minus? Is this not an error? O minus, okay. Okay. So first things to observe. Do you expect this answer to be the same? Surely not, right? You call it a random function, right? Okay. Is there a general trend you can say in this test is always decreasing? Not really, right? Even for this number, right? Sometimes you get accidentally correct, right? Better, okay? But this is something, okay? And this is not everywhere. Even in the same language, same number you call, right? You can see that these two behavior rather different, right? Prandeep's Python, I don't believe is his error. I'll talk about it, okay? It's always negative, rather strange, okay? This oscillate, right? But these also here, right, is accidentally much better. Okay. In this one, okay, it doesn't observe the always minus behavior, right? And this is in MATLAB, so it's calculating a pseudo random number differently. The random number is given differently, okay? So that this is the first one is not even decreasing, right? The error is larger. Okay, so this one is accidentally better. Okay, accidentally better and this. And if you can I combine this result? Do you think? So this is, say, if I only have up to here, okay? Up to here, okay? Are these cases combinable? They can. There's no reason they can't, right? You're calling random number, right? So here I have 1,000 cases from here, 1,000 cases from here, 1,000 cases from here. As long as the random number that they use is not correlated, then you can have 3,000 cases here, right? You have to go through that same calculations, okay? But you can combine them together, okay? And if you plot the error, if this is the log error with your log n, what you should have is something like this, right? Also the samples dangling around a lot, okay? Sometimes it's even, you have this kind of strange dangling, right? But the general trend is this, like in our parameter optimization, right? So if you look at each individual cases, how trustworthy are they? I don't know, okay? But if you do enough of them, the general trend, you have a higher expectation that your answer is correct. Okay, that's all there is. Okay, so this show you the power. Okay, in a way, if you don't know pi, this is one way to calculate pi. It shows you all the limitation. It's very, very slow. Right, you need a lot of cases, right, in order to get a reasonable estimate. In your beginning of your project 1, if you remember, okay, even your execution time to get to the 20th digit correct doesn't take you like more than 2 seconds in your computer. Okay, you just have to deal with the precisions and all the other things, right? Here that you have to wait even for the error still in the 4th digit. And if I ask you to estimate, okay, if you want to have enough confidence that the number you get have 10 digits of confidence, only confidence, you don't know that is real, you can use the square root of n to give an estimate. Remember that it's not, you only have a confidence, okay? You don't have the real answer. So put in von Neumann's own word, okay? Monte Carlo is like, I can get an error bar of an unknown thing. And the important thing is, I need to understand the error on the error bar. Okay, this is von Neumann's own words, okay? I can give you a confidence estimation about an unknown problem. Equivalently, I give you that error bar, okay? But my error bar has error. Okay. But it's still much better than not knowing anything, right? It's literally you don't require to know anything about pi, right? You just that I know that this area is pi, right? How do I get pi? I can use test cases to get pi, okay? So let me stretch your thoughts, okay? Can I get a same number with this? And throw in dots. Can I do that? This area now is 4. I need to return the count divided by 16, okay? Instead of divided by, not 4, yeah. So that's, you can calculate the probability, right? So this is area 4. This is pi over 4. Can I get an estimate of pi of this? Yes, I can. It's just slower, right? There will be more cases you are rejected, right? That don't contribute the calculation of your pi, okay? But can you do this? You can, okay? Can I pose another problem in something like this? Okay, I calculate more efficiently, okay? I know the area of this guy, okay? And I generate, okay, according to another rule to accelerate the process. I can, right? So if I know a little bit more about the properties, okay, your penalty of not knowing it is only reflected in the way it converges, okay? The square root of n is always true. It's just that there is a prefactor, okay? The original distribution's standard deviation, okay? So in the case of this, you get the correct pi will be the same, but it will be converged slower. So you are wasting more cases that's not the correct sample that you need. Okay. So in Monte Carlo, okay, this is one way to use Monte Carlo that I don't know the distributions. Okay, I don't know is the pi or things, but I can use a rejection rule. This is a rejection rule to know what is the legitimate variable, and I can then understand that mean of that legitimate variable. Okay. So, but if you know more, you can do much better. Okay, so these are the 4 known methods of making it better. Okay, is something that's okay. Control variates. Okay, you actually know the mean. Okay, you just don't know its distribution, so you can use that known mean to do something. Okay, sometimes you the physical laws, right, saying that you are throwing electrons to understand your circuits. Okay, but your KCL give you the average number, so you actually know the mean. You just don't know the noise. Okay, so these are called the control variates. If you know more about that things, you can use that, okay, to accelerate your Monte Carlo. This is called the antithetic variates. Is that you know something that's similar. Okay, that if you are doing electrons, saying that, but that's too hard to get experiment. You do billiards. Right? You do experiments on billiards. Okay. And then you can, by the understanding of the billiards, you can make the acceleration of the sampling. Okay, important sampling I just show you. Okay, if you know that what area is more carry a more statistical relevance, focus on sampling in that. Okay, important sampling. Statistical implications is that many times I want to know the border cases. That's more important, okay, like the nuclear reactor, right? To know that it can normally operate is far less important than I know when it will explode. So I'll try to generate cases that's close to that explosion conditions, okay, and assign the statistics correctly, okay? So the parameter space, I have some understanding, but you test cases that's less likely to happen, okay, less likely to happen, but you normalize it correctly with a statistical amplification. Okay, so these are the 4 methods usually do for Monte Carlo method. Okay, I cannot finish for sure Monte Carlo method in one lecture. Okay, so I'll come back on Monday to tell you more about how in a more realistic problem, okay, that you can use Monte Carlo. Okay, 2 things I'll pose to you for you to think about. Okay, 2 things I'll pose to you, just by the hacker example. Okay, hacking example. Okay, in this, what is necessary? Okay, if you have a random number, okay, for any problem, how do you use that random number to generate a test cases of a given problem? Okay, you can choose your given problem of optimization or even parameter extraction or something. How to use that? Use this known random number to cast into a problem that you don't know. Okay. The second is that just using this example. Okay, if I know a little bit more about this problem, can I make this convergence to be faster? Okay. If I know more about the property of this, okay. Can I propose me a method that this can expected to converge faster? Okay, you're doing Monte Carlo, so it's never true answer. Okay, you are expected to be better. Okay, come back to the Monday lecture. Okay. Finish this and quoted from John von Neumann himself. There are many known problems. The only solution today is Monte Carlo, okay, because of the complexity. Something that's